Lesson 4.7, normal force, acceleration, and inclines. And on the worksheet, you number just number 1 and number 3. Now, this is something that really it's just it shows you how to connect the lesson we did before on the making inclined planes, acceleration, and working that into some kinematics problems. So I don't always spend. It depends on what the chapter is, what the time looks like. If we're going to spend a whole lot of time on this or not, but I definitely want you to know more how to do this, and probably like for example, I'll do A and B. Probably B is the most important one between A and B for me right now for where we are. So in 4.7, but both of them you gotta know how to do. And I could throw one of these on a quiz or something. I'm just telling you, you're not gonna have a whole lot like A. I can say that there could be a little bit on there on a test or quiz. So I don't consider that to be. I don't want to put a whole lot of time into that because we have a lot to do in this chapter, and it's a kind of a minor, but something I don't want to skip. It says you have a 950 kilogram bowling ball at rest, is released, and begins to roll down a 37-degree hill. Calculate the velocity of the ball after 3.75 seconds. So, there's different ways to draw the inclined plane. I think last time I did it the other way. Had it going in the other direction. And that's one thing on the worksheet I forgot to kind of point out. Maybe I did do that on there. You kind of want to be able to do it in both directions. I can't remember how I did it. I think I did it. Did I do it this way? Or did I do it the other way? Let me think. I did do it this way in the other one, I think. So I'll do it the other way. I'm not sure. It doesn't matter. You can take a mirror and just draw it the other way. So we'll draw the triangle this way. All right? Just because sometimes you might see on a quiz or test a diagram drawn that way. You could always look at it in a mirror if you had a mirror, and then if you wanted to redraw it or something. Okay, so here's a bowling ball at the top. We'll just put, and it says it is 9.50 kilograms. Then it says, when it says at the top or on it, whatever, I don't want to put it all the way to the top. It's going to mess my little triangle up a little bit. I'll go a little bit higher. This will probably, it's still not going to do good. Oh well. Here's the bowling ball. More than halfway up. You don't want to do halfway, or well, you could do it halfway. I'll just put it right there. It doesn't really matter. Okay. Now, remember, so it's at rest. So maybe you're at the hands on it, then they release it. And on the worksheet, you're only going to do number 1 and number 3 on the problems. Number 4 is a very good one if you wanted to try and figure that out for a challenge problem. But 1 and 3. Okay, so we want to figure out what is going to be the velocity as it rolls down the hill for 3.75 seconds. What will it be after that time? We know this is 37 degrees, the angle. 37.5 degrees, sorry. 37.0 degrees. And then I want to draw my little diagram, triangle here. So remember, force vectors. The weight, gravity, is going to pull straight down here. Now, for this problem, what I need to know is acceleration of gravity. I know what gravity is. If you want to put G, in fact, I'll put G there. You could put A right there. We'll put G or A. I'm going to put A because we're going to be doing kinematics. But we know that the acceleration is 9.81 meter per second squared. Okay? Now, I want to draw a line perpendicular to the surface. That means 90 degrees coming straight out until I match where that arrow is, right about there. And now I'll draw another line parallel to this that goes down that way. So it's not too perfect, but you can just kind of, over and over with it. All right. So if this is, that's 90 degrees because that comes straight down. We also know that this angle, remember, will equal the theta angle. If you don't remember that, go back and look at the video that came before this. So that is also 37 degrees. This is acceleration of gravity, 9.81. We'll call that one AY and AX. Now, so it will not accelerate, as I mentioned in the last video. It's not going to accelerate at 9.81. Now, if I were just to take that bowling ball up here and just drop it straight down, or just pull it off the side, like knock it off the side of the slide this way, like push it out and boom, if it comes out, it's going to fall down at 9.81. So A is 9.81 meter per second squared. Which acceleration do we need? It's going to be going down the hill. We'll just go down to here. We'll just put it right there. Just say it went from there to there. And the time was 3.75 seconds. And it started, we knew the initial velocity as it started to roll, initial velocity is 0 because it was at rest. Okay, we're not going to push it down. If we did, we'd have to tell you what the initial velocity was from the push. So it started at 0. It it slid for that long. It rolled. It rolled for that long. The final time was 3.75. So what is the final velocity down here? We don't know, okay? But we know the acceleration in this direction. A is 9.81, but do we need AX or AY? You only need AX in this picture, okay? AX, the one that's parallel right here, that will be the X component. So to find AX, if I know A, then I will use sine, cosine, or theta. We'll think sine, cosine, or tangent theta, of sine or cosine of theta. So you say, okay, sine will be opposite over hypotenuse, cosine adjacent hypotenuse, and of course tangent will be opposite over adjacent. So it'll be sine. Sine of theta will be AX over A. Now you could put G if you wanted to. Some books will do that anytime you're talking about gravity, but since it's a kinematics, I'll keep it with A, and you'll see in a minute why. But so sine of 37 degrees is going to be AX divided by 9.81 meter per second squared. So the sine of 37 is 0.602 is AY over 9.81. So multiply that times 9.81. You get 5.90 meter per second squared will be AY. It's good to put the unit in that answer at least. I know I didn't throw it all into all these. I put usually the first time I plug it in and then at the end just to make sure. There's almost never any changes in physics with units, but not like chemistry and AP chemistry. But the thing is, you still want to write it in the first step, just in case something didn't match, and you hopefully could notice that, like a little warning light there. All right, now to find the velocity, we'll look at the kinematics equations. Remember, I told you in this chapter, I mainly look at this equation. That's the number one I like the most, and then my least favorite one is this one. And what's the easiest one is this one. A equals V final minus V initial over time. And guess what? You can use the easiest one for this one. They want to know what is the final velocity. If I know the initial is 0, the time is 3.75, and I know the acceleration is 5.90. So I'm going to plug that in right here. 5.90 is equal to, we don't know the final, but we know the initial was 0 meter per second, and the time was 3.75 seconds. Make sure I did not pick any wrong numbers in there. Okay, so all I got to do is multiply this times it, and that's it. 5.90 times 3.75, 22.1. Does it fit down there? I guess it just barely makes it. 22.1. So just multiply. You know, I don't really show you the math of all this, but in case you need to see, this times 3.75 equals this times 3.75. And that gives me 22.1 meter per second equals the final velocity down the slide. So next time you go to a playground, and you can actually figure this out. Now, interestingly, how could you measure the angle if you're in a playground? If you wanted to know a little bonus, what you could do, well, if you could at least measure the length of the slide, or how far you're going to slide, just say from there down. We'll do the whole slide, we'll say. Do the whole slide. The length of the slide, and let that be C, like on ABC. C squared is A squared plus B squared. You don't have to do this bonus, measure the length of the slide, and measure the height of the slide right there. And if I know that, if I know those two, I'll then be able to figure out what A is. Okay, so I know A, B, and C. I measure those two, measure that. Then, remember, the angle, the sine of 37 is, in this case, B divided by A. Or, the inverse sine -1 of B over A would be that angle. So that's how you can find the angle without using any kind of protractor or measuring it. You could go out there and just measure the length. Now, you're assuming that that's 90 degrees, that the ladder goes straight up and it's not like bent or something. Okay, all right, that's the first one. And I told you, this is the one where you could expect, you know, maybe there'll be one problem like this on a quiz or test. I'm not going to put a lot on this one. But the next one is more important. And for sure you'll see it, or it'll pop up in other questions. Sometimes I have to clean off that eraser if you wonder, like sitting there hitting that thing on the stand here. And it's hitting the floor. But this chalk I bought, this new chalk, is anti-dust chalk. So it's supposed to be a little bit better. So, all right, B. Okay, so for this one, let's see, I did that way, so I'll do it this way for the other one. I'll go this way for that diagram. Uh-oh. Doesn't look perfect, but oh well. The normal force always acts perpendicular to the common surface of contact. So I already went over this lesson, you know, in the intro lesson. I think I've got all the details of it. This will be a short one. I'm almost got it done here. D. Calculate the normal force for a 5-kilogram clock. I picked a clock, so let's have that old. Maybe I'll put a little picture here of a little stand, and is that how you make a clock? And then put some arrows on it. It looks clocky now. Clockish. Okay, clock. Oh well. A 5-kilogram clock. So it weighs 5 kg. And yes, I am well aware that when you're doing some of the problems, I got a little bit bored with writing things like, so I started to change into like some strange objects and some strange people that you used to read on the problems, the strange characters that do these weird things. So when you read the problems, you'll think, wait a minute, a bunch of animals and stuff. I tried to make it more interesting. He said just the car drives east for 20 miles per hour for 3 hours. Another, I don't know. I didn't want to do those boring ones. Okay, here we go. Now, for this, calculate normal force. Oh, it's also a 37-degree plane. That makes it a little bit easier, but oh well. All right, so the angle is 37 degrees. And let me make a little diagram again. So I'm going to bring that down. And then remember that I have to have one perpendicular. Oh, I can just barely fit it. And then one parallel. And it doesn't matter if it's perfect or not in your diagram. But I know that angle on the top will also be 37. It's going to be theta. Now, they want you for A to calculate the normal force. So remember, anytime two objects are in contact with each other, the normal force is the force pushing them together, the force of contact. Like if my hand is here, but it's getting opposed by the other one or whatever, well, the normal force, like a support force, it's always going to be the force perpendicular to the surface. So, like if I put an object here on the board, the normal force would be the support force. Gravity force is down, F weight of the calculator goes down, but then my hand, my hand holding it up, it would be the support force. Now, as I angle it, notice, we'll be able to talk about that later on, about where it starts to slide too, because you're overcoming friction at that point. But as you angle it over, the normal force changes. Obviously, it doesn't have the same force holding it up to oppose. Well, here's a better way to say it. Right now, I'm angling it. Gravity is not able to overcome friction. Gravity is not able to pull it down. The normal force is sufficient. Okay. Well, I hate to say it that way because when I get to my lesson on friction, there's a friction force and a normal force we'll get to. But anyway, all you know is that at some point, the normal force lessens and the friction force cannot be overcome. So that's really how it goes, and it slides down. Okay, So this is your weight force, and then this one is Fx, Fy. I mean, if you want to call that Fx and Fy, you can do that if you want to, if you want to change the letters. But just make sure you're consistent in your calculation. So if I want the normal force would have to be equal to Fy. Now, technically, the normal force will go in the opposite direction. So it's up here, but it's going to equal out Fy. So how much is this clock being pressed against the surface? Well, gravity is pulling it this way, Fy, against the surface, and the normal force is supporting it. If you put something, let's just say that you made a little slide and you made it out of like really like paper, like or how about cards? Like when you build a house out of playing cards. What if you made like something like this, if you even could, put one card sideways and made a little ramp like that? Okay, if I put like a clock on it, it's probably just gonna, boom, it's just gonna break right through. So in other words, that's not gonna, the normal force, it's not gonna be able to support that thing at all. Okay, it's just gonna break right through it. So anyway, the normal force, that can't happen if you're gonna do a real calculation. It would be useless. But in this case, Fy and F normal should be the same. F normal should be Fy. I mean, it's the opposite, of Fy. As I told you, we're not really doing anything with direction here, so you don't have to worry about making it negative. All right, so here we go. Let's find the normal force. The weight, first of all, the weight of the clock is mg, is 5 kilograms times the g is 9.81 meter per second squared. So about 50, it's 49.1. Kilogram meter second squared, as I showed you in the last video, becomes newtons. So that one we know. Now we just got to figure out what is Fy, and we know the angle. So think about this. Sine of this angle is Fx over the weight, but cosine would be Fy over the weight. So Fy would be cosine of 37 times mg, or times F weight. So, okay, but the way I'll write it down here, cosine of theta will equal F weight, which is mg, over Fy. It's probably good to know, because this can happen in standardized tests, that if you're doing, like if we do them this year or not, I'm sorry, F weight, they could write cosine of theta equals mg over Fy. This is also true. I mean, F weight is mg. But sometimes physics people, they like to put up all the letters in and solve the whole problem, and then at the very end they put the numbers in. I don't really do it that way. But I'm just telling you, in case you see a multiple choice question, you say, which is true, well, that's true. They might not write that, but that is true. This is more likely to be something they'd ask you on a A, B, C, D, E, which is true. Cosine of theta is mg over Fy. Sine of theta equals mg, or tangent of theta, or tangent -1, cosine -1. So they can give you a bunch of choices, but that's the one that will be true. Cosine of theta is adjacent Fy. Oh my goodness! And what a bad fella. Bad fella. That's really, they would all be wrong. Cosine, I didn't even think about it myself. I mean, I didn't good enough. Fy over F weight. I know some people were saying, Vela, I was telling you, I was yelling it out. Yes, I make mistakes, people. I make mistakes, I know, and I'm sorry. Oh, that could be, oh no, that would be, there it is again. As I'm saying, I make mistakes, I'm making a mistake. All right. Sorry, that is correct. Okay, so cosine is adjacent Fy over F weight. So cosine of theta is cosine of 37 equals Fy over 49.1. So 37 cosine is 0.799. Equals Fy over 49.1. So 0.799 times 49.1 is 39.2 equals Fy. So that means that the normal force will be have to also equal 39.2 newtons. I mean, one could say it's negative and that won't be positive, but it's being the force in between of contact in between the surface of the slide and the clock, supporting it that way, is 39.2 newtons. Okay, and let me check. What's the next part of this question? Yeah, I'm sorry. I'm glad I caught my mistake with that part. B. See, I don't have the answers or anything here. I'm just doing it off the paper from my mind, but I caught myself there. What force is required? Oh, what force is required to keep the clock from sliding down the hill? Okay, so Fy is the normal force, or equal to the normal force. We'll say 39.2. So the force to keep it from sliding down the hill, like if I wanted to put a force this way and hold it in place, that will be the opposite of Fx. Whatever Fx is, because Fx is the component of gravity pulling it down the hill. So this would have to be the same equal but opposite direction. So Fx, I have to match the force of gravity, and I hold it right there, and it will keep it from going down the hill. Now, I mentioned this in the last video, and this is also the force that you would apply if you want to push it up the hill. It's interesting. So if you keep that force just a little bit more, you apply a little bit higher than the Fx, it'll start to move up the hill. And if you keep Fx on it, it will constantly go up. So it's easier to push somebody, like a real heavy person. You can push that person up a ramp, and you can even make the ramp a lot less inclined. You can make it a really long ramp. It's easier to push something up a really long ramp that's inclined than it is to lift them up to that height. So anyway, that's just an interesting thing. So Fx is the force required to keep it from moving, or if it is moving, it's the force required to keep it at a constant speed. And that will come up in a later chapter as well. So let's calculate Fx, and we'll have that answer. So this time it will be sine of theta is equal to Fx over F weight. Okay, I didn't mess up that time. Opposite over hypotenuse is sine. So sine of 37 will be Fx. Make sure it looks like an X and not a Y though. Okay. Over 49.1 was your weight. So then this will be the same that we saw. 37 sine is 0.602 is Fx over 49.1. You don't have to show me all of these steps. You should show me at least this step, and if you want to jump to the answer, that's okay with me. If you have that, you show me all the numbers plugged in correctly, and that will at least give you part credit. And then you just take that and multiply. Find sine. So it's 29.5 newtons equals Fx. So that, even that answer in itself makes it easy to see. Like this clock, the mass, if I want to lift it up, I got to lift up with 49.1 newtons. That's not very heavy. But I got to use 49 to lift it straight up. That's to match its weight, or to hold it in my hand, 49. But if I put it on a ramp, to keep it from sliding down the ramp, all I got to do is add 29 newton. So that makes it a whole lot easier. 29 newtons uses less energy, less force. A small child could do that easier than trying to have them lift the 49 one. Okay. All right. So that is all. So work on, as I said, just number 1 and number 3 on the worksheet, and we'll move on. I'll see you.